Hello, students, and welcome. Today, we are going to break down the topic of spherical mirrors and make it really simple to understand, especially for your board exams.
Let's start with something you've probably seen every single day. You know, the curved surface of a shining spoon? It acts just like a spherical mirror. By the end of this session, you'll know exactly why your reflection looks so different on the front and the back.
So, this is our roadmap for today. We'll start with the basics. Then we will get into the details of how concave and convex mirrors work. After that, we'll see how they're used in the real world, and finally, we'll do a quick summary for your exams. Let's begin. All right, first things first. Let's quickly revise the fundamental concepts of spherical mirrors. Getting these basics right is absolutely the key to mastering this entire topic.
It's actually quite simple to remember. Think of a concave mirror. Its reflecting surface is curved inwards, just like a cave. And a convex mirror? Well, that's the opposite. Its surface bulges outwards.
Okay, so to really understand how these mirrors form images, we need to get familiar with their basic parts. Let's look at the three most important reference points you will find on any spherical mirror.
These terms are like the basic geography of our mirror. First, we have the pole, which we call P. It's simply the geometric center of the mirror's surface. Then there's the center of curvature, or C. Just imagine the big, hollow sphere that the mirror was cut from. C is the center of that sphere. And finally, the principal axis. That's the straight line that passes right through both P and C.
Okay, now for what I think is the most important point for image formation, the principal focus. We call it F. This is really where all the magic happens.
Now watch this carefully. Look what happens with a concave mirror. When light rays come in parallel to the principal axis, the mirror reflects them all inward. See that? They all come together, or converge, at one single point. And that special point is what we call the principal focus.
Now, because the light rays are actually physically meeting at this point, we call it a real focus. You could literally place a piece of paper right there, and if the light source was the sun, the paper would get so hot it would start to burn. This also means you can project the image onto a screen.
A convex mirror, on the other hand, does the complete opposite. It takes those same parallel rays and scatters them, making them diverge or spread out. If you look closely, it appears as if all these reflected rays are coming from a single point behind the mirror.
But are the rays actually meeting there? No, of course not. Our brain just traces them back to this imaginary meeting point. And since the rays don't really meet, we call this a virtual focus. You can never, ever form an image from a virtual focus on a screen.
Now, here is a simple but very, very important relationship you need for your exams. The radius of curvature, which we call r, is always double the focal length, f. This tells us that the principal focus, f, is located exactly halfway between the pole, p, and the center of curvature, c. Please remember this formula, r equals 2f.
All right, now for the really interesting part. We're going to see how a concave mirror forms different kinds of images. And the fascinating thing is, the image changes completely depending on where you place the object. Let's go through the main cases one by one.
Let's start with a very unique case. What happens if we place the object exactly at the center of curvature, C? Well, look, the image is also formed exactly at C. Now let's look at its nature. It is a real image. It is inverted, which means it's upside down, and it is exactly the same size as the object.
Okay, now let's move the object a little closer, somewhere between C and F. Watch what happens to the image. It is now moved farther away, beyond C. It's still real, and it's still inverted. But what about the size? Notice, it has now become enlarged or magnified.
And now for the special case. This is how a shaving mirror or a dentist mirror works. When we place the object very, very close to the mirror, between the pole P and the focus F, something completely different happens. No real image is formed. Instead, a virtual image forms behind the mirror. And this image is erect, meaning upright, and it is enlarged.
So, after all those different cases for the concave mirror, you'll be happy to hear that the convex mirror is much, much simpler. It is very predictable.
Let's look at the ray diagram to understand why. You can see how the rays from the object reflect and diverge. Our eyes then trace them back to form that smaller virtual image behind the mirror.
So, this brings us to the most important rule for convex mirrors, the golden rule. No matter where you place the object, the image will always be virtual,
It will always be erect, and it will always be diminished or smaller than the object. Always. It never changes.
Okay, so we've learned the theory. Let's connect this to the real world and see where these mirrors are actually used and, more importantly, why they are used. Concave mirrors, as we saw, are used for focusing light. By placing a bulb at the focus, they take all that spreading light and reflect it out as a powerful parallel beam. This is perfect for car headlights and torches. Convex mirrors, on the other hand, are used for seeing a wider area. They give an upright, smaller image, allowing drivers to see a large area of the road behind them in a small side mirror.
And now for the final part. Let's put everything together in one place for your final revision before the exam.
This table summarizes everything we've learned about the concave mirror. I would suggest you pause here and review it, or even take a screenshot. It shows exactly how the image's position, size, and nature change as the object moves. It is a perfect tool for studying.
So, as you can see, understanding these patterns is the key. It's not just about exams, it's about seeing the physics in the world all around you. Now that you know the rules, think about the question on the screen. Why are convex mirrors perfect for security in shops? The answer uses the exact same logic as a car's side mirror. Thank you for watching and keep exploring.